Okay, so I want to talk about we'll do some applications now of the Black-Scholes formula, and then we'll also just talk about the Greek letters we had talked about, and I'll go over some examples using MATLAB, just to give some insight about how the Black-Scholes formula and the Greeks interact with each other. So, for example, if we had, our goal was to calculate the price of a 3-month European option, put option, on a non-dividend paying stock. So non-dividend paying stock, that's a stock that the owner of the stock doesn't get payments every quarter or every year from the company. They just buy the stock and then at some later point sell the stock. So there's no payments that come out along the way. And if we had a dividend paying stock, it wouldn't be too difficult to put that into our formula. But we'll go with the simpler version right now, non-dividend paying stock. And the price of the stock is $50, and the current price of the strike price is $50, which means it's at the money. It's not in the money yet. If it starts, since it's a put option, if the stock price started dropping, we would start being in the money for this put option. And the risk-free interest rate is 10%, and the volatility of the stock is 30%. So the volatility of the stock, just a reminder, is that would be like our sigma. This would be one standard deviation over a course of a year of where you would expect the stock, how much you would expect the stock price to deviate away from its expected value. So 30% is a pretty high number. That would be like comparable to what Google is now these days. And okay, so here's our variables for the question. So this is just a recap of this sentence. And then when doing the Black-Scholes computation, we wanted to come up with evaluate two variables, the D1 and the D2, which most textbooks refer to it as. The D1 was this formula, the log of the stock divided by the strike price plus the interest rate minus sigma squared over 2 times the remaining time until the expiration of the stock. So this is the expiration time and T is the current time. You might see in some textbooks this is just considered little t, or it means the amount of time remaining until expiration. Then divided by sigma times the square root of the remaining time. So for this concrete example with these numbers, you punch these numbers into this formula and you get this computation, which then goes on to equal 0.2417. Then we also wanted to calculate D2. The variables D1 and D2 are used in calculating the put and call prices. So D2 is calculated as taking D1, so that's why they're numbered 1 and 2 to let you know this one should be calculated first. And D1 minus sigma times the square root of the remaining time. So we had this answer from D1, goes right here, and then minus 0.3, which is our volatility, and times the square root of the remaining time. In this example, there's 3 more months to go, so it's a quarter of a year. And that gives us our D2. Now we can just plug it into the put formula. There's a call formula and a put formula in Black-Scholes. And we plug it into the put formula, and the put formula says we use K times e to the minus R times the remaining time. Then take a normally distributed variable, the z-score of a normally distributed variable with a mean of 0 and a standard deviation of 1, and we put negative D2, that's the formula for the put. And then we subtract the stock price with the remaining time. The stock price, that should be at the current time, which is T, right? In this formula, little t is the current time and big T is the expiration time. So the current time, and then a normal distribution of negative, the variable calculated as D1. So this calculators for these normal distributions, or you could look them up on those charts if you have the old math textbooks, and then you get these numbers. You would get these numbers. And then this comes out to $2.37. So the Black-Scholes formula for a put option on this stock with this information, 3 months left to go, would be $2.37 per share. Okay. Just a side thing, if the stock happens to be paying a dividend, All a dividend means, gonna come back later, like 40 minutes? Okay, thanks. Dividend later means, I'm sorry, a dividend would mean that instead of using the interest rate of let's say, the interest rate would be 0.1, we would add to the interest rate, no, I'm sorry, we would add to the, let's see, we would have I'm sorry, we would want to subtract off the present value of the future payments of the dividend between now and the expiration of the stock. So for the next 3 months, we would want to take away the dividend in this case. The dividend was $1.50. So if the dividend, in this case, I believe the dividend was, dividend in this example, I didn't write this out. The dividend in this example was $1.50 was being paid 2 months from now. So what we ended up doing was taking the amount of interest for 2 months from now and times the current interest rate and said $1.50, calculating back to the present value would be this amount of money gets subtracted from the current stock price. So it's basically, it's effectively like the current stock price is $48.42. So that basically means the owner of the stock will receive that payment, but the person who buys the stock option does not receive any dividend payments. They're just buying an option on the final price of the stock. So all we're really doing is just recalculating the value of the stock as of today, and then using the same exact formula. And you put it through the same exact formula, you'd end up paying a little bit more than before, if the stock happens to pay a dividend. So it's kind of like effectively part of a component of this current stock price takes into account the fact that a dividend is coming in 2 months. So it was artificially high, so that would really make the current value of the stock really being $48.52, which would mean the put option is a little bit in the money. So therefore, the put option is worth a little bit more than if the stock was $50 like the last example. Okay. Okay, so all of the parameters we use to do this calculation are real-world parameters that we can just get. You know, we know what the stock price is. We know what the strike price is. We can get the interest rate, like going to the websites like usgov.com or finding the treasury bills and saying, assuming the US government will never go out of business, that's the risk-free interest rate. And how much time until it expires, we know because we know the date it expires and we know today's date. So the time, the interest rate, the strike price, and the current price are concrete values we can get. Volatility is really, that's kind of the secret sauce of this equation. Where do you get the volatility from? How do you know what is Google's current volatility today? How would you know how much to expect it to be away from the expected value 1 year from today? What would it be based on? How volatile it was in the past? How volatile it was for the last week? How volatile it was 2 years ago? I mean, what would you use? What newspaper would you go to? Where would you look? What website would tell you what its current volatility is? There really is no example. But there really is no source that provides that. So there's the concept of, well, the implied volatility. What is the volatility that the Black-Scholes equation, what value for volatility is the Black-Scholes equation saying if you punched in all the other concrete inputs? It would then tell you what the implied volatility is. So the way to one way to calculate what the market thinks the volatility is to set up that equation like we did on the last example. Set up this equation, calculate the number, but we don't know what to put in as input for sigma. So we could do like an Excel goal seek to figure out what the sigma is. By one thing we do know is what the current price of the stock option is selling for. So all the real data we can get is everything but the volatility. We even know what the market is currently, what the last sale for a stock option was. And so we can reverse engineer and find the volatility. So that's basically what they call the implied volatility. It's assuming you taking the answer to the call price, getting that from the market, figuring out backwards what the volatility is. So the market determines what the implied volatility is of a stock. So one way to see what do the people in the stock market believe a certain stock's volatility is to use the Black-Scholes equation and reverse engineer it, do a goal seek and find the value of the volatility. Okay, so then recall when we were talking about the derivation of the Black-Scholes equation, we talked about what's commonly referred to as the Greeks. So the Greeks are a collection of Greek letters, and they're basically considering the fact that we're calculating the price of an option, and there's about 5 or so parameters that go into calculating the price. We say, well, what if one of the parameters was to change? What effect would that have on the call price or the put price? So delta ends up being the change on the call price with respect to the change in the stock price. So it'd be kind of like taking a partial derivative with respect to one of the input variables and assuming all the other input variables remain constant. That's the way partial derivatives work. And then saying, what's the slope with respect to that angle? Okay, so the stock price was, the change in the call price with respect to the stock price was considered delta. The second derivative of the delta, and this is probably the most interesting one that people would look at, the change in the underlying stock price affects the change of the call price. The second one was delta. Delta was the second derivative, gamma was the derivative of delta, which means gamma is the second derivative of the stock price. So the second derivative of a function gives you insight into like the convexity or concavity of the first derivative. So in other words, if we were to say the delta for a stock was a certain value, that means, well, let's say for example, the delta of a stock was 0.5. So that says if the stock goes up $1, the call price goes up 50 cents. Okay, now for how long is that true? Well, we want to look at the second derivative. If the second derivative is 0, that means that statement will be true for a long period of time. If the second derivative is very high, that means that statement that every dollar the stock goes up means the call goes up 50 cents. That's only true for a very small area, and then that delta would start changing. Okay, and then the volatility, if you remember, we have a Greek letter, vega, which is actually not a Greek letter. It's just, it sounds like a Greek letter, but it's not a Greek letter. But it begins with a V, and volatility begins with a V. So I think they just needed a Greek letter that began with a V. And are there any Greek letters that begin with a V? I don't think so. So I think they just made up a Greek letter, vega. So just remember V, volatility, and vega both start with V. So the change in the stock price with respect to the change in the volatility is what vega is. Theta, which begins with a T, it maps to time, which also begins with a T. And so that one they could use a Greek letter that actually begins with a T, so that's good. So we could say the theta of a call option is the change in which the stock, the change that the rate of change of the call price with the rate of change of time is measured by the Greek letter theta. Okay, and there's a theta for a call and a theta for a put. And then interest rates, so I guess the big word is the rate, not interest. The rate, we need a Greek letter that starts with R, so we use rho. So rate and rho both begin with R. So rho of an option is the rate at which the call price changes with respect to the rate at which the interest rates change. Okay. So they all kind of map letter for letter, right? V and V, T and T, R and R. Delta, let's see, D and S. D. What could have been D? Delta. D derivative? I don't know. Well, D is the most, delta is the most common Greek letter to mean a rate of change, so maybe they just took D. It would have been nice if they picked a Greek letter that began with S, I guess, for stock. Well, you can do call options on more than just stock. So you could do call options on anything. So I guess they just used delta because that's the most common Greek letter for meaning rate of change. Okay. So now, delta hedging, for example, this would be like making use of these Greek letters. Okay, a delta of, say, 0.7. Let's say there's a certain stock, certain call option, certain strike price, amount of remaining time, certain volatility, certain interest rate. And we calculate that delta is currently 0.7. This means that when the price of the stock increases, or increases by a small amount, the price of the option, the price of the call option, will increase by 70% of that small amount. So that's kind of like saying, well, if the underlying stock went up $1, the call price is expected to go up 70 cents, if delta is calculated to currently be 0.7. So, for example, a short position of 1,000 options has a delta of minus 700, if this was the case, if it was 0.7. So you can make this delta neutral by going out and purchasing 700 shares. So that's basically saying if you have 1,000 call options, you're worried about the stock going down. If the stock goes down, your call values will start going down at 70% of the rate at which the stock goes down. So if you bought 70% of much shares, then any change in the underlying stock would get canceled. So you would be hedged, meaning you're avoiding taking a loss. You might be avoiding getting a gain, but you're avoiding, when you're hedging, you're avoiding taking a loss. And you could delta hedge, what would be called delta hedging, by buying 700 shares. For any small fluctuation in the price, you won't gain or lose anything. A larger fluctuation in the price, this might no longer be true, and the way you see that is to look at the variable, the value of gamma. Okay. Let's see. Okay, so this was a true story. I was down at the, I don't know if you know the bar, the Mix, down in Long Branch. I was there last year, and there was a guy in the bar, and I kind of just know him from being there. And he knew I teach this material. So he had his cell phone, and he had like Scott Trade or one of those trading apps on his phone. And he said, oh, I'm looking at this one stock. It was a Citibank stock. This was last December. And it was a Citibank stock, and he said the stock was currently selling for $4.59, and his app on his phone told him that delta was 0.05. And it also told him that gamma was 0.466, and it told him theta. So it didn't give the rho, and vega. Maybe you have to hit like more information to get those. But it gave the stock price, and it gave these three of the Greeks. So he said to me, and he looked up on Google, what does delta mean? And he looked it up and said, well, if the stock price changes by $1, then the call price should change by 5 cents. That's the definition of it, right? So the call option expires on Friday, December 17th, which was 2 days later. So there's not a whole lot of time left. I'm sure that the theta would be extremely high because every day that goes by, this thing is getting killed. But the call option was expiring on Friday, 2 days later, and with a strike price of $5. So we are 41 cents before making any money. It has to go 41 cents just for us to then start being in a position to make money. And the option was currently selling for 1 cent. So for 1 penny, you can buy a stock option, and you have 2 days to go above $5, and it's currently selling for $4.59. Not very likely to go above $5 in the next 2 days, but if it shot way up, you could become rich by paying only 1 penny. So it might be something someone might want to buy. So what he said to me was, well, since delta is 0.5, if the stock price went up $1 in the next 2 days, you know, if it went from $4.59 to $5.59, then the call should go up 5 cents. If the stock goes up $1, the call goes up 5 cents. That's exactly what delta means. When you calculate the value of delta, a stock going up $1 means the call goes up 5 cents. So he said, well, if that's true, then wouldn't it mean that if the stock went from $4.59 to $5.59, the call price would go from 1 cent up to 6 cents? So then I'm like kind of looking at it going, wait, and he kind of knew this didn't make sense, because if the stock price before it expired went to $5.59 and the strike price is $5, this option is worth at least 59 cents. It's worth 59 cents plus, depending on if we have a little more time, it could even make even more money. So it would have to sell for more than 59 cents. It would be selling for like 61, 62 cents if it went up to, if the underlying stock went up $1. But he's saying, I'm waiting for this to happen so I can buy the options at 6 cents and then cash them in for at least 59 cents. And the reason why this statement is not true, even though delta claims it is true, the reason why this statement is not true is because this delta of 0.05 is only valid for a small range. It's not valid for a range like $1. It's only valid for a small change in price. And the reason you know it's only valid for a very small range is because the second derivative, gamma, is high. If this was near 0, then this delta value would be valid for a long period of time. But it wasn't valid for a long period of time. It might only be valid for a change in the option price of a couple of pennies. I'm sorry, a change in the strike price. So if it went to like $4.62, well, let's say hypothetically it went up 20 cents. So it went from $4.59 to $4.79. Then it's possible that the option would go up a penny, maybe to 2 cents. In fact, it might even go up 3 cents, because then the delta would start changing for even a 20-cent span. This delta would then change so dramatically that it's not even valid for a 20-cent span. But it's certainly that statement that for every $1 the stock goes up, the call goes up 5 cents. That's not true for a range of $1. It's true for a very small range. And if you want to get a sense for how big the range is that it's valid, you look at gamma. So that's really the point of gamma. The gamma of an option is really the delta of the delta. So the gamma of the option is the position, the rate of change of delta with respect to the asset's price. So for example, if a gamma is 10%, would indicate that when the asset price increases a certain small amount, delta increases by 10% too. So if the price of that, if the price of the Citibank example, if the stock price increased by 10%, then the delta would increase. So let me go with this. if the stock price increased by 10%, so if you added 40 cents onto this, delta would increase by 10% times 46, by 46% times 10%. Delta would increase by, instead of being 0.5, it would go up to 0.9. Oh, okay. So, I just want to go over some examples using MATLAB. So MATLAB is basically, yeah, we said a MATLAB was stands for math, a matrix. MAT is matrix, LAB is laboratory. So it's basically a tool. Mostly, it was originally generated around multiplying matrices and vectors together and then drawing graphs based on those computations. But it's been very popular used in the financial world. And the creators of MATLAB have added the Black-Scholes equation and computations for calculating each of the Greeks. So what we can do now is we can use the MATLAB function. For example, we have a Black-Scholes, BL for black, S for Scholes, delta. And basically it takes in the parameters that we're looking for, and it tells us what the value for the Black-Scholes delta will tell us if we have a strike price of, if we have a current stock price of 50 and a strike price, let me make this 50. We have a strike price of 50 and an interest rate of 12%, and the time remaining till the end of, till expiration is a quarter of a year, so let's say it's an option that's 3 months out. Volatility is 30%, which is pretty high, but reasonable, and the yield, in case there was a dividend, was 0. So this is a zero, the stock that's not paying a dividend. So what we can do in MATLAB is you bring up a formula and then you can just run it. So just a reminder, if you're a MATLAB user, you hit this go, this green arrow, and it runs this code, and it's basically one line of code, and its output should show up here. So let me just run this. And basically, we have, what this is basically telling us, it's calculating the delta for us. So for a call option, the delta would be 0.6, and for a put option, it would be negative 0.3. So what is the meaning of that? So the meaning is basically, if the stock price is currently selling for $50 and the strike price is currently at $50, that means it's at the money. If the stock price starts going up, the call option has value. If the stock price starts going down, the put option has value. And the delta is basically trying to say, well, if the stock price went up $1, how much would the option go up? Well, if the stock price went up $1, the delta is saying it would go up 0.6. So whatever the current price of the call option is, let's say the call option was currently selling for $5. If the underlying stock went up to $51, the option would go up 60 cents in value. Assuming nothing else changed, meaning like time's not changing. So it would have to like kind of go up that much in an instant. A puts delta, why is it negative? Well, a puts delta is basically saying if the stock price started going up, that's going to hurt the put buyer. The put wants the stock to go down, so of course it's going to be negative. And then if the stock price started going down, its value would diminish, but it wouldn't diminish as much as the stock price going up. Now, if we changed the strike price to, let's say, just to make it interesting, if we change the stock price to 75, the strike price is 75, the stock price is still 50. So if the strike was changed to 75, what effect would you think that would have on the call delta and the put delta? So the call delta, if you owned a call and it was $25 out of the money, meaning it has to grow $25 just for you to then start making money. If the stock price fluctuated, how much would that cause the call to fluctuate? I'm not asking you to try to figure out what the number is, but how would you, what would it be with comparison to when we were at the money? Now, if we were to be $25 out of the money. The call delta should drop. Obviously, the price going up helps us, so it should be a positive number. But the call delta should drop. And if we're $25, if the current start price is $25 below the strike, that's great news for the put option owner because they're already in for $25. If the stock was to then go up $1, so a put option would be selling for how much in this scenario? Where the current price is 50 and the strike is 75, it would be selling for at least $25 because you could buy it today and immediately cash it for $25. So it's going to be selling for at least $25 and might even be more because it's an earning potential. So it might be selling for $28, $29 for an option. And if the stock went up $1, how much would that hurt the price of the option? That would hurt it by almost $1 because 95, 96% of the price of the put is the fact that it's in the money. And there's a certain small percentage for the ability to gain even additional money. But a put option, actually time is not working on your side. Time is more time for the stock to do what it's expected to do and go up in value. So this, I would expect the call delta to drop, and I would expect the put delta to go very high, like near negative, like negative 0.9. Like for every dollar the stock price goes up, a call option that is $25 in the money is going to lose almost the whole dollar. So let me hit the run button. And so, oh wow, I didn't expect it to be that high, but I expected this to be low, but not this low. This is an option, $25 out of the money. So if the underlying stock price went up $1, we're only going to go up not even 1 penny, and not even 1 penny, 3/4 of a penny it would go up. So the news that the stock went up $1 is like almost no news to this person who owns the call option. The person who owns the put option, every dollar the stock price goes up, they're saying, oh, I just lost 99 cents. So if the stock price in this case went from 50 to 51, the option would drop 99 cents. So almost every dollar the stock price goes up is almost a complete dollar loss to the put option owner. Okay, so that would be an example of the delta. So I'm just going over this for intuitive reasons. And then what was the next one? We said gamma was the derivative of the derivative. So if we had, again, we'll do the same example where we have the stock price is currently 50 and the strike price is 50. And the other things are all the same, quarter of a year to go, 12% interest, 30% volatility, no dividend. The gamma for this one, this would be the rate of change of the rate of change. The gamma in this case is 0.05. So that's a relatively low number. If gamma is 0, that means delta is valid for a big range. So this is, you know, this is kind of good for a pretty good. This worked for a pretty good range, because gamma is low. Now gamma, what would make it more convex or more concave? So if we were to change the strike price to 75, what would that end up doing? What would be the intuition here? For calls and puts, how big of a range would our delta be valid for? So for example, when we had a strike price of 75 and a current price of 50, the put option looked like for every dollar the stock went up, would be at almost a 99-cent loss to the person who's holding put option, would we expect this rate of change, with the window of which that statement is valid, would we expect that to increase or decrease? And I would think that the gamma would go down, because when we're that far out of the money or into the money, the delta is valid for a larger range of a change in the price. So a $1 change, it would be approximately 99 cents, and even a $2 change would be a hit of approximately 99 cents. But when you're near at the money, your gamma goes up higher. So, yeah, this is pretty low. But this is saying 0.0028. So that means when we're at that strike price of 75, our delta is good for, that's a valid statement for a pretty good range. It'll be true for a while. And the stock gets up to be about $55, $60, then all of a sudden that delta is no good anymore. It has to be recalculated. And you'd have to redo your delta hedging too. Okay, what else is interesting? Vega. So Vega begins with a V. Since Vega begins with a V, we're talking about a change in volatility. So with a strike price of 50 and a strike price of 50 and a current price of 50, same numbers as before, Vega would be, what would we expect Vega to be? Vega is a change in volatility. So now the thing is this, we don't really know who tells us the volatility changed, because volatility is basically calculated by implying it from the stock price. But if we somehow decided that the volatility of a company is expected to go up, some analysts at our company decided that the Google stock is going to, starting tomorrow, its volatility is going to go up based on some information. Again, this would be like our secret sauce. This is what makes our firm different from all the other firms. We do volatility calculations different than they do. All the other prices we're just getting straight out of the newspaper. So if we decided that volatility starting tomorrow for a certain stock is going to go up, how much would that affect the underlying call, the call price? So let's see what we would do then. Well, before I hit the button, what would we expect it to be? Well, it's a relative concept. So the Black-Scholes Vega would be, if the volatility doubled, the option price should grow by a certain magnitude. I wouldn't even know how to guess this. But okay, so it's by a ninefold. Wow. So if the volatility doubled, the volatility doubled of the stock, the Vega says that the stock price would fluctuate by 9.6 times that. Okay, so now if we change the strike price to, we seem to be using this example a lot, changing it to 75 and just seeing how that affects these Greek variables. If we made the stock price 75, that means for a call we're $25 out of the money, and for a put we're $25 into the money. So look at it from the point of view of a call. There's one Vega for calls and puts. Look at it from the point of view of a call. If the volatility of the stock went up, the value of the option would go up because we have a greater chance of getting into the money. It would go up, so it should be positive. I think Vega should always be positive. I can't think of a scenario where a stock gets more volatile, starts hurting options, so Vega should always be positive. And the volatility increase won't help us too much. It'll be good news, but it won't help us as much as when we're at the money. If we're at the money and then all of a sudden the volatility of the company starting tomorrow is expected to go way up, that's great news for us. If we are $25 out of the money and then the volatility we hear or we calculate that the volatility is gonna start increasing. Well, it's good news, but it's not great news like when we were at the money. So Vega should be positive but lower than 9.6 if we priced it out of the money. So it dropped to, oh wow, it dropped a lot. So it dropped to 0.52. Vega was 1/18 of what it used to be. Okay, is there anything else interesting? Rho is sensitivity. Rho begins with an R and rate begins with an R. So this is the change in the calls and puts will have different rows. Because Black-Scholes gives us two answers, so you know it has two different answers. So rho ends up being, if we did the same computation, rho would end up being, rho for call is 0.6 and rho for put is negative. So if the interest rate started going up, that would cause the stock price's expectation to go up, because stock prices kind of track the interest rates. So an increase in the interest rate for an option that is at the money would cause a 6.6 times increase in the value of the stock price. So interest rate increase would cause stock call options to go up in value. And then put options would be hurt because if the interest rate goes up, the stock price is expected to go up, which is bad news for the person who owns a put option. So the put row would be a negative number. And these are pretty big magnitudes. And then if we were to increase the, if we were to change the strike price again to 75, then our call row, an increase in interest rates really doesn't help us too much because we're so far out of the money. So this dropped by a lot, but then the row for the put went up dramatically. Any effect of the interest rate, now the put is $25 into the money, so any effect on the interest rate for row would really hurt the put person. An increase in interest rate is really going to cause a big loss, an 18 times loss to somebody having a put option. And then there's also, we did Vega, right? So Vega, I guess I should have done them in alphabetical order, I guess it doesn't matter. Okay, so, and then the theta begins with a T, so theta is change in time. And if we were, strike price is 50, and current price is 50, we get the call theta is negative. So strike price is 50, price is currently 50. Time ticking is bad news for the call option, which is why it would be negative. Pretty high, because we're kind of getting near the end, we have a quarter of a year to go. And time ticking is bad news for the put option, because the put person is hoping the price will drop, and they're running out of time. So as time goes positive, as time ticks forward, the value of both of these is dropping. Time kills both of them. Now, if we made the strike price 75, put it way out of the money, the call option is $25 out of the money, time is running out, now time is killing us, right? So the time will not affect us as much because we're kind of out of the game to begin with. So the theta for the call, time running, I mean, we're already at a very low price. Time running is still killing us, so it should be negative. Time is going to hurt us. But the put, how much, for a put, that's $25 in the money. is time ticking good news or bad news? It's telling you guys. Okay, anyone have a guess for time ticking? Is that good news or bad news? If you held a put option that could pay you $25 right now, a European option, and time was ticking, would you say this is good news? Like, are you hoping to kill the clock, or do you want more time so maybe you could even get more into the money? At this point, time is the change in your option. If time increases, the change in your option, it's almost like you're hoping to kill the clock. So in this case, time would be, let me just show the very positive. So in this case, wow, in this case, time ticking is good news for you. As time's ticking, the value of your option, which is $25 in money, actually starts increasing because it's considered that your opportunity to lose your gains is going away with time, because stock prices are expected to go up. So if you were $25 into the money on a European call, you're kind of just sitting there saying, I hope the clock gets killed. So time ticking is actually good news for you. As time's ticking, you're going up 8 times as much in value.